Hello, in this video we're going to look at eigenvalues and eigenvectors. Now, I know those words sound pretty complicated, but they're not too challenging to understand, and they're a very important area of matrices, very important study when you're talking about matrices. So in many applications, a matrix is actually considered an operation. As such, we often talk about applying a matrix to a piece of data or a set of values. For example, in computer graphics, matrices can be used to rotate or reflect images. So in that sense, the matrix won't be the data, the matrix will be the operation we're applying to the data. Now, obviously, there may be a matrix that holds the data as well, so matrices can take on multiple representations. But for right now, we're going to consider the matrix as doing something to the data rather than being a box storing data. So instead of considering points, right now we're going to consider vectors. A vector for our purposes is just a line drawn from the origin to the point. So for example, here is the point 2, 3 as a vector, because we go over to 2 and 3, then we draw a line from the origin to that point and put a little arrow on the top. Now let's consider this vector 2, 3. What will be the vector after a rotation of 90 degrees counterclockwise? Well, let's look at Desmos to see how this rotation would look. So you can see the vector at 2, 3. And what I mean by a rotation is, well, we take the vector and we swing it around. So maybe we swing it to there, or maybe we swing it over here. And if we're going to rotate it 90 degrees, well, that would be right about there. For an exact value, we should probably type in the rotation as pi by 2. And so an exact rotation of 90 degrees, or pi by 2 because we do it in radians, we can see takes us to the point -3 and 2. And that should make some intuitive sense. If you think about this vector being rotated 90 degrees, what ends up happening is there's a bit of a switch there in the coordinates. The 2 goes to the y and the 3 goes to the x, and then the 3 gets made negative. So hopefully you can visualize what's happened there. We've got this rotation of 90 degrees. However, you might not have been able to guess that the vector 2, 3, after the rotation, becomes -3 and 2. Maybe it makes sense afterwards, but you might not have been able to visualize that initially. And so it would be helpful if we had a matrix that would rotate for us. Well, in 2 dimensions, the matrix of rotation is this: cos, negative sine, sine, and cos. This matrix will do a rotation for you. So let's perform the same calculation using the rotation matrix. So let's take a look. We wanted to do 90 degrees. So theta equals 90 degrees. Our rotation matrix would then be cos of 90 minus sine of 90, sine of 90, and cos of 90. So we evaluate each one of these. Cos of 90, of course, is 0, and sine of 90 is 1, so we get -1 and 1 there. So this is our rotation matrix. Now what we do is we take this matrix, and we go ahead and multiply it by our vector. So I'm going to do this up here just for space. So we take our matrix, 0, -1, 1, and 0, and we multiply it by our vector 2, 3. Now we stack that vector as a column because the only way to multiply a 2 by 2 matrix would be by a 2 by 1 vector. We need to have, of course, these dimensions matching up. So we do the multiplication, and we get 2 times 0 is 0, -1 times 3 is -3, 2 times 1 is 2, and then 3 times 0 is 0. So there we go, we got the same thing as over here. So let's try determining the matrix of rotation for 180 degrees. So theta would be equal to 180 degrees. We would do cos of 180, negative sine of 180, sine of 180, and cos of 180. So we use our unit circle values to give us -1, 0, 0, -1. And so if we needed to do a rotation by 180 degrees, we could go ahead and just multiply by this matrix. So let's determine the matrix of rotation for, let's say, 45 degrees. We're going to apply it to the vector 2, 2. So let's go ahead and do cos 45, negative sine 45, sine 45, and cos 45. Those are a bit messier in terms of unit circle values. They're all actually root 2 over 2. So we're going to get root 2 over 2, negative root 2 over 2, root 2 over 2, and root 2 over 2. Alright, so we're going to take that matrix of rotation, and we're going to multiply it by our vector. Or I should say multiply our vector by the matrix of rotation. So then our vector is 2, 2, and let's do the multiplication. So 2 times root 2 over 2 will just be a root 2. And then 2 times negative root 2 over 2 will give us a negative root 2. Here we get a root 2 plus a root 2. So that gives us a total of 0 and 2 root 2. So that's our new vector. The point, or vector, 2, 2 was rotated to the new vector 0 and 2 root 2. Now, if you try to visualize this, it should make sense. The point was over initially at 2 and 2. If we rotate that 45 degrees, well, 45 degrees is going to land us right on this axis. So the whole vector is going to now end up on the y-axis, which makes sense because our new vector here is completely on the y. But you might have thought, oh, well, shouldn't it be then like 0, 2, because it'll be all on the y? Well, not entirely. This vector is not actually of length 2. It's 2 on the x and 2 on the y, which makes the vector actually of length, well, we got to do a little bit of Pythagoras. The radius, or the length of the vector, would be equal to 2 squared plus 2 squared, which is 4 plus 4, or root 8, which is, of course, 2 root 2, just like we see here. So it does make sense intuitively. You could have figured out this value using some basic trigonometry, but again, it's nicer and I think a little bit more fun to use matrix multiplication. Now in the above examples, we demonstrated how matrices can perform an operation, and matrices can transform vectors in all sorts of ways. We might ask a question like, are there any vectors in the xy plane unaffected by a transformation, specifically rotation? In other words, are there any vectors that are quote-unquote invariant? And the problem with asking this question is that the entire point of a transformation is to move vectors around. If you think about it, when you rotate vectors, they move all over the place. You're doing a transformation. So it might be a bit too much to say what vectors are completely unchanged. We might need to relax our question a bit. And so a better question would be, when performing a transformation, what are the vectors that are only stretched by the operation? What are the vectors that they might still be transformed, but they're not transformed too much from their original place? They're just stretched instead of being moved around too much. So let's consider this matrix right here. This is going to be an operation. It's not necessarily a rotation because, of course, this didn't come from the cos, negative sine, sine, and cos, but it is a matrix, and so it's clearly doing some type of transformation. And let's see what happens when we apply it to these vectors down here. So we're going to go ahead and multiply. We've got 5, 1, 4, and 5. We're going to multiply by the vector 0, 1. Well, that'll give us 5 times 0 is 0, so then 1, and 5. So if you notice, this is a radically different vector. The old vector had nothing in the x and 1 in the y. The new vector's got both x and y. This one just became a 1, this one became a 5. Very different vector. Let's try this one. 5, 1, 4, 5, 1, 2. So 5 times 1 is 5, plus 2 is 7, and then 4. 4 plus 10, that'll be 14. Well, this vector looks kind of similar to the other one. This is 1, 2. This is 7, 14. Notice how this is double that. This is double that. In fact, if you were to try to get from here to here, it looks like you could do maybe times 7. If you times by 7, 1 times 7 is 7. Yeah, 2 times 7 is 14. Maybe maybe this vector is only stretched. Well, let's look at one more. So we've got 5, 1, 4, 5, 1 and 3. So it'll give us 5 plus 3 is 8, and then 4 plus 15 is 19. Well, again, this is triple that one, but 19 isn't triple 8, so it doesn't look like those are related. Now, it seems like this one here, this vector was special. It's only a multiple of the other vector. If we're talking about stretching is an English word. In mathematics, to stretch something means to multiply it. So this vector has just been multiplied by 7, so it appears that this vector is stretched, and only stretched. And let's see if Desmos can help us visualize this. So here we have our original vector in red, our point 0 and 1. And we can see that that point has been moved to 1 and 5, which is what happened during our transformation. Let's type in maybe our third point, 1 and 3. So the point 1 and 3 have been moved up to 8 and 19. And you can see from both of these, especially on this second one, that the two vectors are not parallel. They're not a stretched version one from the other. They're offset a little bit. And if we actually just move this point, we can see that there are all sorts of weird transformations. For example, the vector 2.45 and 0.4, it's definitely been transformed. It's got a little bit of a rotation. It's been stretched way out there. This is definitely a different vector than what we started with. But if you look here, you can kind of imagine maybe putting the two vectors, it almost looks like if we were to bring a special value right in here, that they might line up. And so if we try that second vector that we had, which was 1 and 2, well, now we go to 7 and 14, and if you notice here, the transformation, it gave us a new vector. It went from the red vector to the blue vector, but the new vector is just a stretch of the old one. It's just been made longer, stretched out, which is not the case for tons of vectors in the plane, but for this specific one, it indeed seems like it's only been stretched, which is interesting. It's interesting that that happened to this vector, and we want to explore this more. Is this the only vector? Are there other vectors? We want to try to figure out, because this seems like a special vector. So we want to notice that the vector 1, 2 has only been stretched by the matrix, and it's actually been stretched by a very specific amount, by 7 times. Well, let's take a look at this matrix operation applied to 3 and 6. So 5, 1, 4, 5. We're going to multiply 3, 6. Well, we'll get 5 times 3, so 15 plus 6. That's going to be 21. And 3 times 4, that'll be 12, plus 30. It's going to be 42. Well, if you look here, does the same rule apply? Are these related to each other? Well, 3 times something, it looks like 3 times 7 will give 21, and indeed 6 times 7 will also be 42. So yes, this vector is also stretched. Yes, it is stretched. And again, it's stretched by that weird amount, by 7. It seems like the number 7 is coming up on this matrix. It's coming up exactly, well, stretched 7 times bigger. Well, is that the only stretch factor? Let's try another one down here. Let's continue to investigate this matrix. So 5, 1, 4, 5. Let's multiply into the vector negative 1 and 2. So that's going to give us negative 5 plus 2 will be negative 3. And then negative 4 plus 10 will be 6. Well, this looks like a bit of a different vector over here. It looks like this is giving us times 3. And then 2 times 3 is 6. So we seem to have this, now there's another number. Are there lots of numbers? Well, if we had times 7 on that one and times 3 on that one, what's going on? What's going on here? And so we want to notice that again, it is pretty neat. We've got this vector, -1 and 2. It's only been stretched by the matrix, but it's been stretched by a very precise amount, and it's not 7 times. This time it's been stretched 3 times. So where do the numbers 7 and 3 come from? Somehow this matrix of 5 and 1 and 4 and 5, somehow it gives the values 3 and 7. And it's really not clear where those come from. I mean, I guess you could say maybe, 4 minus 1 is 3 maybe, but 5 minus 5 is not 7. 5 times 5 is 25. It's not clear where these numbers 3 and 7 come from. But in fact, there is a way to discover these special numbers 3 and 7. So as a definition, an eigenvalue is a special scalar, special number, which we give the symbol lambda, the Greek letter lambda, such that AV equals lambda V for some non-zero vector V. Now note, V is going to be called an eigenvector. So in our above example, these numbers 3 and 7, we call them eigenvalues because we take our matrix, we multiply by a vector, we get back a scaled version of that vector, just a multiplied, and the special number that we multiply by was either 3 or 7. So the lambda there is 3, or the lambda is 7. But again, how do we find that? We've just given a definition. Well, there's actually a formula. To calculate the eigenvalues of a matrix, we have to solve the following equation. We have the determinant of A minus lambda I. Now, where in the world did that formula come from? I'm going to give you a bit of justification for this. So our formula starts off with this. This is how we found our eigenvalue. We took our matrix, we multiplied it by a vector, and we got back our vector with a scaled version, so a lambda v. What I'm going to do is I'm going to solve this by moving everything to one side. So I get AV minus lambda v. Well, I'm going to go ahead and factor out the v. So A minus lambda v equals 0. So next up, this gives you, I guess according to your factoring knowledge, that A minus lambda should equal 0. We're setting this factor equal to 0. But we've got a bit of an issue here. A is a matrix and lambda is a regular number, so a matrix can't equal a number. So what we have to do is stick in a little extra piece, which is I. Now remember, I is the identity matrix, and so I times anything doesn't change it, and by putting this I in here, we have a matrix and we have another matrix. So this keeps both of our pieces as a matrix. So A minus lambda I equals 0, because this equation doesn't really make sense to have a matrix and a real number somehow equaling 0. And then our last step is to say, well, if this thing equals 0, what we could do is we could take the determinant. And A minus lambda I would then equal the determinant of 0, which of course you could think of that as what is the size of 0, what is the length of 0, that's just going to be 0. So our final formula then is A minus lambda I inside of a determinant equals 0. Again, this is a bit hand-wavy, but it should give you some justification for where the formula is coming from. So it's time. Let's go ahead and calculate the eigenvalues for A. Again, we know them ahead of time. We're suspecting these special numbers to be 3 and 7, but let's see if we can come up with an explanation for where they came from. So A minus lambda I is our initial part of the formula, which would be 5, 1, 4, 5. And we're going to subtract lambda, and then our identity matrix, remember, is 1, 0, 0, 1. So when we do that lambda, we can multiply it in, which gives you lambda 0, 0, lambda. All right, well that's going to give us 5 minus lambda, 1, 4, 5 minus lambda. Next up, we need to do the determinant. So now we do the determinant of 5 minus lambda, 1, 4, 5 minus lambda. Remember, for this we multiply these two entries, so 5 minus lambda, 5 minus lambda. Then we subtract multiplying the other two entries, so 4 times 1 is 4. And this thing we want to set equal to 0. Well, it looks like we're back in algebra land. We can go ahead and expand out by using FOIL. So this will give us 25 minus 5 lambda minus 5 lambda plus lambda squared minus 4 equals to 0. So we'll put that lambda in front, minus 10 lambda. 25 minus 4 is 21. And, well, hey, that looks like a basic factoring question. This is like x squared minus 10x plus 21 equals 0. It's just instead of an x, we have a lambda. So let's continue that on over here, make a little bit more space. And so we have lambda squared minus 10 lambda plus 21 equals 0. Two numbers that multiply to give 21 and add to give 10, you bet they are -7 and -3. Which means lambda equals 7 and lambda equals 3. Look at that. Amazing. We found the two special values, the two eigenvalues, that are the stretch factors when you do multiplication with this matrix. Again, not every vector will be stretched by these amounts, but when you find that special vector that's only stretched, it has to be stretched by exactly 3 or exactly 7. So let's go through that process again with this new matrix, and let's find the eigenvalues. So we'll do A minus lambda I to start. So replacing that with the matrix we have, we would get 1, 1, 4, 1 minus lambda times 1, 0, 0, 1. So 1, 1, 4, 1 minus lambda 0, 0, lambda, which would give us 1 minus lambda, 1, 4, 1 minus lambda. So next up we take that matrix and we calculate the determinant. So we do the determinant of 1 minus lambda, 1, 4, 1 minus lambda, which gives us 1 minus lambda, 1 minus lambda, minus 4. Of course, this thing needs to equal 0, so we'll expand this. 1 minus lambda plus lambda squared minus 4. So lambda squared minus 2 lambda minus 3 equals 0. So we're looking for two numbers that multiply to give -3 and add to give -2. I'm thinking lambda minus 3 and lambda plus 1. So that gives me lambda equals 3 and lambda equals -1. So those are our special values, our special scalar values, our eigenvalues. Now, there are a bunch of wonderful properties about eigenvalues. We don't have time to look at every single property, but there are a few interesting ones that are worth talking about. So, for one of them, the sum of the eigenvalues equals the sum of the diagonal entries. Another one, the product of the eigenvalues equals the determinant. So, these are kind of interesting properties about eigenvalues, and so if we put down our matrices that we had before, we had 5, 1, 4, 5. And remember, this had values 3 and 7. Well, if you look at the diagonal, 5 plus 5 equals 10, and 3 plus 7 equals 10. So that's kind of cool. You get this property that you can check your answer. The eigenvalue should add up to the diagonal entries. So the 5 and the 5 should add up to give you 10, and the 3 and the 7 should add up to give you 10. Let's just check that that works with the other matrix as well. So we had the matrix 1, 1, 4, 1. And we found eigenvalues of 3 and -1. So if we look at that diagonal, 1 plus 1 equals 2, and 3 plus -1 also equals 2. So, pretty neat property about eigenvalues. Another remark, the product of the eigenvalues equals the determinant. So let's look at that one here. Well, our eigenvalues were 3 and 7. So 3 times 7 equals 21. What would be the determinant of this original matrix? 5, 1, 4, 5. That means we got to do 25 minus 4, which, oh, sure enough, is 21. Again, an interesting tie-in there that apparently determinants and eigenvalues are these relationships. We can try it over here with this one. So we can do the determinant of 1, 1, 4, 1. That'll be 1 minus 4, which gives you negative 3. Sure enough, negative 3 would be the same thing as 3 times negative 1. So some interesting properties there. But now returning to our very first example, we had rotated by 90 degrees with the matrix 0, negative 1, 1, and 0. Now, if we do this rotation, it doesn't seem like any vector would be only stretched. Again, imagine that. You're rotating by 90. Any vector is going to be rotated because everything's been rotated by 90 degrees. There's going to be no vector that's only stretched. Everything's rotated. So when you look at this matrix, you think to yourself, you know, I don't think there would be any eigenvectors. I don't think there would be any vector that's only stretched, and so I don't think there would be any eigenvalues. There'd be no special stretch value because nothing would be only stretched. And that would be a very reasonable assumption. So let's, just for fun though, see if we could calculate the eigenvalues. We'll do the same process. We're assuming that it'll be impossible because we don't think anything would be only stretched when you do a full rotation by 90 degrees. A minus lambda I will be 0, negative 1, 1, 0 minus lambda times 1, 0, 0, 1. So 0, negative 1, 1, 0 minus lambda 0, 0, lambda, which will give us negative lambda, negative 1, 1, negative lambda. So let's do the determinant of negative lambda, negative 1, 1, negative lambda. So we've got a lot of negative signs there. Negative lambda times negative lambda is lambda squared. Negative 1 times 1 is negative 1, and we have to subtract it, so plus 1 equals 0. Well, let's go ahead and solve that. We can move the 1 to the other side to get negative 1. We can square root both sides, and we get plus or minus the square root of negative 1. Now, hopefully you remember from the complex unit that we're totally able to do this. Lambda then equals to plus or minus I. What in the world does that mean? Well, initially, you might argue that this has no solution. And so you're right. There is no real number solution to this, which means there is no real eigenvalue. This matrix does not have any real numbers that are not affected by the rotation. But apparently there are complex values, complex eigenvalues. So just for fun then, let's apply this matrix to this vector. We're going to need a complex vector here, so let's do the vector negative 3i and 3. So we're going to take 0, negative 1, 1 and 0. We're going to multiply it by the vector negative 3i and 3. Bet you didn't think you were going to be doing complex numbers in the matrix unit. Well, here we have 0 times negative 3i, which is 0, and then negative 1 times 3 is negative 3. 1 times negative 3i is negative 3i. Alright, well, does this thing somehow look like it's related to this? It looks kind of like a scalar multiplication, but kind of not. There's like some new negative signs introduced, and it's hard to say, but apparently I, or negative I, is our eigenvalue, our stretch factor. So let's try it. Let's do our original vector, negative 3i and 3. And let's multiply this by maybe I. Well, if we multiply by I, we're going to get negative 3i squared and 3i, which would give us 3 and, well, 3i. That doesn't look quite right. So let's go ahead and instead try multiplying by negative I, our other stretch factor. Maybe it's this one. Well, when we multiply here, we're going to get negative negative makes positive, so positive 3i squared. And then negative 3i, which gives us negative 3, negative 3i. So this one over here, this didn't work out. This was not, the stretch factor wasn't I. But this one did work out. Notice this is the same as this. So apparently, there was a stretch factor. This was stretched. The stretch, the amount it was times by, it was times negative I, which is kind of interesting. We were able to do a stretch factor. There is a vector that is unaffected by the rotation. It's just stretched. But what in the world does this vector look like? How could we draw this vector and visualize that it's only stretched? Well, here's the problem. We have a vector that's been apparently stretched. The vector is 3i, 3. But this vector has two components, and each component is a complex number. So this component here has two parts, right? A real and an imaginary. And this component over here has two parts, a real and an imaginary. Which means if we were going to graph this on a plane, well, we would need 4 parts. 1 axis, 2 axis, 3 axis, 4 axis? What in the world? How would we draw a 4th axis? We would need 4 dimensions. Yeah, you got it right. You would need 4 dimensions to visualize this. Which, let's just be honest right here, as 3-dimensional creatures, you're not going to be able to visualize a 4-dimensional vector. It's just not possible. But what you are able to do is the math. And this is just a bit of a taste of where you can go in this area of mathematics. You can start to combine complex numbers with matrices. And so you can have these matrices that act on complex vectors. And you can discover strange things, like even though when you think about a rotation, every vector is rotated, there are complex vectors that are not rotated by a rotation. They're only stretched. They're eigenvectors, and they're stretched by associated eigenvalues, and those eigenvalues are complex. And so there's a whole area of mathematics you can study here. You can't necessarily visualize it, but that's part of the power of mathematics, is we're now able to go beyond visualization. Here, you can't really visualize what is happening, but mathematically, we were able to show that this vector was only stretched. And so this is the power of mathematics. It allows the human mind to go beyond the simple visualization, to go beyond 3 dimensions into 4 dimensions or 10 dimensions or n dimensions, and to solve problems that would be otherwise impossible to solve using only visualization. Now, that's not to say visualizing is bad. It's a very useful technique to be able to have pictures of things, but we want to be able to go further than that, and in some ways mathematics allows us to go further than we could have ever gone before. So here are some exercises. You can try some matrix of rotation questions as well as some eigenvalue and eigenvector questions. I really hope you enjoyed this section on matrices, and if you want to learn more about matrices, I definitely encourage you to take linear algebra. If you take enough linear algebra, you'll be able to take it where the matrices and the complex numbers begin to overlap, and there's some beautiful mathematics to be studied here. So I hope you enjoyed this video, and I hope it piqued your interest in some of these concepts, and as always, thanks for watching.